take the camera.
Who?
Just take the camera. Why didn't you call me? Mr. This is my office. You want to take anything from my office, and this is from text, not for. If you want to take anything from my office, call me.
Can you start recording this stuff?
No, you take it. You use it. You take anything from my office.
Maybe the opposite is better.
Only him.
What?
Who's take? No. Yes, yes, yes. It's clear, clear. You can see it.
Oh, this clear. Okay. I see in the small picture.
No. Yes.
Can you slice it?
Oh, sorry. I'm sorry.
Oh, I see.
The same guy, sorry. I just picked it up a couple of ones.
Yeah. And some of them repeat, so
That's why
you can freelance.
I kind of like the order two, though. The one that that was my job. Organizing the order. Trying to take something. But you're right, some of my notes were kind of versions of technology.
Yeah. Amazing how the technology has evolved. In old days, you have huge cameras.
Yeah.
Now it's
Microphone.
iPhone.
That's what she started. بسم الله والصلاة والسلام على رسول الله Good afternoon. Thank you, everybody, for joining us today in this installment of Science Hub. As a podcast brought to you in partnership with the King Abdulaziz City for Science and Technology, CACS, and the King Salman Science Oasis. Special thanks to His Excellency Dr. Waḥة for his continued support and inspirational leadership. I'm honored to begin our Science Hub titled Science and Space Exploration by introducing our distinguished speaker, Professor Charles Elachi. It is my great pleasure to introduce one of the world leaders in space exploration. As previously director of NASA's Jet Propulsion Laboratory hosted at Caltech, during his tenure, he has also served as vice president and professor in electrical engineering and planetary science at Caltech. Professor Elachi led JPL for more than 15 years during the period of solar system exploration, earth science, and space-based astronomy, as well as development of the Keck Space Telescope. In 8+ years with JPL, Professor Elachi has been a leader in developing the field of spaceborne imaging radar, served as team leader on many space missions, and he has co-authored more than 230 publications and is the owner of several patents. The recipient of numerous honors, he was named one of America's best leaders by the U.S. News and World Report. He is also an asteroid named after him in honor of his contributions to planetary exploration. With more than 5 decades of research and leadership, this has given him a unique perspective on the development of technologies, specifically space technologies, to pursue an exoplanet exploration, and we all look forward to hear what he has to share today. Thank you, Professor Elachi, for joining us, and I would like to begin our session with a series of questions that we have prepared. What inspired you to pursue a career in space science, exploration, and research?
Right, first, I want to say I'm delighted to be here and to visit CAS. I always enjoy coming to visiting them and to work with our colleagues and friends at CAS. The inspiration is since I was a kid, I grew up in Lebanon. Since I was a little kid in a small village, I was always fascinated by the sky, these beautiful stars and so on. I was wondering, is there some people living on those planets? But also, in addition to that, I was fortunate. My parents always encouraged me to get a good education. They felt that education is something important. I lucked out that the schools I went to, particularly the professors of physics and math, they was always very, in a sense, funny that they made science really pleasurable to the class. So between that combination of these things, I got excited about doing science. So after I finished my high school in Lebanon, I went to France, got my engineering degree, went to the United States for my PhD, and the timing was perfect. The first year I was in the US, Armstrong landed on the moon. So that was, it's like it was a Saudi astronaut. Everybody is kind of excited and watching them. And the same thing it was at that time. I was at that time about 20 years old. And I was just, wow, we can go to space, we can travel in space. And that kind of got me, engaged, in science and technology and the space. I didn't know that I'd become the director of JPL at that time, but I was fascinated and really excited about these activities. So that's how I got into the business.
It sounds like a mix of curiosity and exploration.
Absolutely, and keeping your curiosity as you evolve in life is extremely important. And there is a saying that I love which says, you don't lose curiosity because you get old. You get old because you lose curiosity. So you just have to stay curious in all your life.
And you mentioned you're curious about life on other planets. So throughout your experience, what has kind of been the answer to the question? I know it's debatable.
I mean, that is a very important topic to really understand how life evolved on our planet. Is it something common? In the solar system or in the universe around us? Because the laws of chemistry and physics and biology are the same. So you wonder why is there life here in every planet, around us, if there is the right environment, the temperature and so on. And if we discover life somewhere else, that would be amazing for us as humans. And if we don't find life, that would be equally amazing. Why is there life only on this planet, but not other? So that's one major goal in our exploration now, both to look at possible life in our solar system, like on Mars or on Europa, but also to look at the planet around other stars and see are there planets similar to our planets, where you have oxygen, you have atmosphere, the temperature is the right temperature, there is biological activity. So this is one of the major goals that now we're doing in our space exploration.
Very nice. Very interesting insight. What do you believe are the most significant challenges facing the space industry today? What are the most significant challenges facing the space industry today?
The space activity. Well,
if you could list them, maybe.
Yeah, well, it's all challenging, but that's what makes it exciting.
Yeah.
Because there are challenges that we can do. One key challenge, particularly in our solar system, is the fact that it takes so long to go to another planet. Like, for instance, the moon is not very far; it will take 3 days. But to go to Mars is like 9 months. To go to Jupiter is like 5-6 years. So propulsion is one of the biggest technological challenges now. Is to really be able to move much faster. That's what I'm doing now. And people are coming up with amazing imaginative ideas, like maybe using solar sails, or using nuclear propulsion, or using the sunlight to actually push it onto that. So there is a lot of innovation which is going on in developing that technology. And who knows, there might be suddenly some brilliant Saudi who might come up with an idea, as a new idea. Because if you go back, 100 years ago, we had no idea we'd be able to travel, across the solar system. And here today, we do it fairly common. So I would say that's one of the biggest challenges is the propulsion and how fast we can travel.
Interesting. So from your experience in terms of these innovative propulsion systems you mentioned, which one stands out to you as more promising? Which one should we pursue?
Which one should I bet on?
Yeah.
On knowing that. I think the solar sail is a very, very imaginative idea.
It's more of a mechanical.
No, they are all. It's hard for me to decide, or to recommend one. Even people are going so far out of like talking about matter, antimatter, where you can mix matter, antimatter, and get energy. But I think looking at the near term, I would say using nuclear power to be able, in combination with electric propulsion, might be, at least we know the technology. It's a question of engineering and to make it lightweight, safe, and so on. So that might be, if I have to bet, I would say the combination of nuclear with electric propulsion might be our best bet in the future. But we have to explore all of them because surprises happen all the time.
Interesting. Thank you for sharing that. So what new technologies or techniques are currently being developed to help explore and study space management?
Yeah.
So maybe that is in orbit technology, some of the rovers we've seen on Mars.
Yeah. The thing which have enabled us to move enabled some significant advances is also miniaturization in electronics.
Right.
That made a huge difference. I remember the days where a little calculator barely can do something. Now I have in my iPhone an amazing amount of power of calculation. So I think the miniaturization of electronics has done a huge difference. Technology for telecommunication, the coding. Now we're looking at laser communication in addition to radio communication. And then developing material which is very lightweight, because in almost all of our space activity, we say power and weight are at a premium. So developing lightweight material, miniaturized, using low amount of power are very good. Looking at the future, I would say robotics, artificial intelligence are going to make a significant impact on how do we use exploration, because for many of the places we travel to, except the moon, it takes many hours for the signal to get there because of how far away they are. Therefore, you need to have basically completely independent rovers or helicopters that we are using for exploration, but they have to be autonomous in a major way. So developing this capability and technology for autonomy and somewhat intelligent, maybe not completely independent of us, I think is going to be allow us to make major breakthrough in the future.
Totally agree. I think we've seen some of that in recent Mars missions.
Yeah, yeah.
How do you think our understanding of space will evolve over the next few decades, and what new discoveries do you anticipate?
Well, I mean, clearly the life is a big issue. I mean, the discovery of potential life is a big issue. So now, we have a rover on Mars which is collecting samples, but we are planning to bring back here by end of this decade. So seeing any signature of biological activity, I mean, it might not be life like us,
Yeah.
but if you see any cells or biological activities, then the next question, are these cells or life based on similar as our life here? Like we have DNA, carbon chain. Is it similar or different? If it's similar, then you wonder, is this kind of anywhere it's similar to us? Because we found it on another planet. Or if it's different, then we might learn something new. Maybe life could be based on things other than carbon, or based on other than the typical organic material. But Europa is other place in Enceladus. Europa is a satellite of Jupiter, Enceladus a satellite of Saturn. And we find in both of them, we think there is water below the surface. So it could be maybe an environment similar to the oceans here, and you can find life way deep in the ocean. You find life around volcanic vents. So could there be something similar? And then the next question is that not only could be something similar, is there DNA and their cells similar to ours, or are they different? So I think there will be big breakthrough in the other one is the planets which are similar to ours. If you see something that you would wonder could have life, involved on that. And the other area is going to be technological advances coming, from space, activity. So I could envision over the next decade the kind of thing that we're doing with CACs now about what we call eyes on Earth, and is to be able to every day, every citizen anywhere in the world on their iPhone, they can see what's happening to our environment. The temperature, carbon dioxide emission, methane emission. So we all would become collectively conscientious about what's happening on our environment because of space is allowing to do that. So I think these are some of the examples of the advances we see in the next.
Right, so I've seen the eyes on Earth, and it's really amazing how it's the dashboard really to our planet.
Yeah. No, and I want to emphasize that particularly the Arabic version was done by the Saudi researchers at CAT. And that's a great example of collaboration between the United States and the Kingdom.
I agree. I think it's a great example of transfer of technology.
Yeah. And the researcher at CAT contributed some additional things that we didn't have.
Right.
So we started putting that in our version. Some additional things that we didn't have.
Right.
So we started putting that in our version.
Nice. It's always nice to highlight the contributions that
Yeah.
experiments, planning, space research, and how do we ensure that our models are accurately representative of
Sure. Now that's a very good question because particularly building spacecraft, is it very about it to design it, to actually develop it and get it to fly. And before we used to do, and the other thing is you have to remember, once you launch it, and there is a problem, you cannot bring it back. It's too late, by that point.
Yeah.
So it's important that it's done right. But then, 8 years is a long time to do that. So now we are developing the capability of simulation, modeling, quickly being able to build a model and test them ahead of time. It's going to be extremely important because that will allow us to speed the development. And like if you have a model which can simulate the vibration during launch, so you can design your spacecraft, properly at that time. So yeah, I think modeling and simulation plays a key role. Now, the critical thing is to make sure that the model and the simulation are correct, that they are based on past experience, and so on. So those are going to play and allow us to speed up things significantly than what we had in the past.
In terms of the accuracy of the models, so how do you ensure accuracy, or how accurate do they have to be?
Well, it has to be through testing.
Yeah.
I mean, once you develop a model, then you use it to build something, and then and test it in that environment and find out is it correct. that you have the model was done properly. But once you test it and you verify it and so on, then the model can be used, commonly at that time. And it's important that regularly people look at updating those models to do the simulation, because new activity comes, new material is developed, new electronic is developed, and you want to improve those capability in the model. So it's important to continue to keep updating that model and keep verifying that when you update it, you are the proper things to do that.
Interesting, you mentioned how, like you said, once you do a space mission, it's kind of like a press button and go. So how can we learn from that data gathered, during the space mission to improve the simulated model?
Yeah, no, I think that's a very good point too, because you are always learning,
Right.
particularly as there are advances. So at the JPL, every time we send a mission, after that mission, we have lessons learned. What have we learned from this mission? What worked well? What did not work well? And then we incorporate that in our models or our procedures, of developing spacecraft. So, and we used to say a critical element of the mission is to make sure you have the lessons learned. And it has to be done by the people who worked on that mission. It's not something that come 10 years later and you say, what have we learned? So immediately after we launch and we get started operation, we always work lessons learned. We give them lectures to the new employees who are coming there, or the people developing the models, and we keep updating them on a regular basis.
Nice. So just to clarify, when you mentioned, so the lessons learned, you guys begin once the mission begins, and how long is that process lessons learned?
Well, it's a continuous process. So as soon as we launch the mission, typically it takes us about 2 months to 5 months to test all the subsystems, make sure they are working properly, and so on. So immediately after that, as far as the hardware modeling is done. But as the mission progresses, there are new things, that we do. Like in the case of the rover, some of them have been operating for 10 years. And I can tell you that the software on the rover today is very different than when we launched, because we learned, on operating it, and we keep updating it. We update we have it's not exactly a model, but a copy of the rover at the JPL, and which is identical to the rover, because we use it if there is any problem, on the rover on Mars. Before we send command to fix it, we test it on the rover, so that's part of our simulation, and so to make sure that it's working properly. Then we send the command to it. And there are a variety of lessons. Example, sometimes the rover gets stuck in the sanders. So figure out to extract it, which weeds do you use, do you use it on, a little bit like when you do with your car if you are getting stuck in a sand. And that's part of our learning of how do you get, in your driving, all these things to do that. As we look at the changes in temperature, which part of the rover is being impacted more than others thermally. And that's what we do in our thermal models, to improve. One other thing we found when our models, to improve. One other thing we found when we flew Curiosity is the wheels, which are made of aluminum. As we were driving on Mars, that basically rocks on Mars are very sharp. We didn't expect that, and they are actually puncturing the wheels, which are from aluminum. So we immediately started modifying how do we drive them. And then on the next mission, Perseverance, we actually thickened the walls, of the wheel based on the lessons we learned from the previous one.
Very interesting. It's interesting that you mentioned the replica that we have.
Yeah, that's usually, particularly when you are doing things early. We don't have replica of orbiting spacecraft. For the rovers, which are our first or second or third, we have an exactly identical copy of it at JPL that we use for testing.
Very nice. So just to end this question, in terms of the accuracy of the model, is there a standard way to calculate this accuracy, or is it something it's like maybe the pursuit of perfection?
No, it's not a standard way, but we tend to be very conservative in our case. So when we develop models, we test them and build something based on those models. We test them for at least a factor of 2 more extreme, environment. Like for instance, if we expect the temperature would be going up to, let's say, 200 degrees, we test them to 400 degrees. And sometimes also we test them to 400 degrees. And sometimes also we test model until they break.
Okay.
So we know how far away are we from being at the edge. You don't want to be 2%,
Right.
away from a break.
Right.
50% would be a reasonable place.
So-
If you are very conservative, you go to 100%, that means double doing that. So yeah, we do test the model to, I wouldn't call it accuracy, but to see how far are they really simulating the
Okay.
environment.
Maybe operability.
Yeah, that's what we're thinking about.
What are some of the most exciting upcoming space missions and projects that you're currently working with or that you're looking forward to seeing?
Yeah. There is a spectrum of them. So the one which is the most which we are sending a spacecraft which is going to go in orbit, around Jupiter and study Europa. And that's the one we will be looking at to see how thick is the ice, where is the ocean below the surface. So that mission is going to be launched in October 2024. So it's about a year and a few months from now. So that's as far as going to the outer planet. Then for Mars, one of the most challenging missions is, as I mentioned earlier, we are collecting samples now. The rover we have on Mars is going to collect about 30 or 40 samples. So the next step is to go and bring them back. So that will be required to have a lander, which will land on the surface. Then it would have a helicopter which would fly and collect those samples that we put in little tubes, bring them to the lander. Then we have to put the sample in the nose of a little rocket, launch that rocket in orbit around Mars, and then the capsule separate from the rocket, and then another spacecraft will rendezvous with it and bring the sample back. So as you could imagine, as an engineer, this is going to be very challenging, to be able to do that. That's right. Now, from excitement, it's a mission that we're working, on the data jointly with CARES, which is a synthetic aperture radar. This will be flying in orbit. It will be launched next February, and it will map the whole world, which means also the whole kingdom, every 12 days. And the data will be getting almost 10 terahertz every day. So then the next question is, how do you process and handle that data so to be able to take images around the world? But then the next part is, how do you analyze it? You're not going to have, you would need millions of people to look at all that data. So the idea would be then to develop some kind of artificial intelligent algorithm which will scan the data and then say, I found something interesting here, or something interesting there. I'm seeing subsidence of the water table around Cairo, in Saudi Arabia, or a signature of earthquake happening in some remote area, and be able to bring that to the attention of the user. So the user doesn't have to look at each and every picture, but depending on their interest, would say, okay, this is the pattern I'm looking at. So you develop software to extract that pattern and tell you there is that in that way. So these are examples of some of the challenges that I think are going to be happening in the next few years.
Interesting. It just sounds more like computer programming.
And develop smart software. So it's not, there are two factors. One is to have a lot of computing so you'll be able to look at all the data, terahertz every day. And then the next one is to have intelligent enough algorithm to recognize certain pattern and bring it to the attention of the user.
That seems like a big challenge. Managing, big data.
That's what makes it fun, our business. It's full of challenges.
Yeah, but it's interesting, the big data challenge.
Yeah.
Would this require its own supercomputer, its own server?
Well,
what's the solution?
Yeah, you need a lot of calculation, but you don't have to have it. You can use the cloud. That's one major development which has happened in the last 5 years. I remember the days that for all these missions we had to bring a computer to JPL to know the process. Now we don't use any computers actually. We all do it on the cloud. We buy time on the cloud, and that will provide the capacity that we need.
So there is enough capacity in the cloud.
Yeah.
What challenges have you had working on the cloud, or what are things to be aware of?
Well, when it early started, first there is no, it's like having a computer next door.
Yeah.
So the challenge you have to have, one is to have a link capacity.
Okay.
The other one which worried me a lot when we started using it, we have to have, one is to have a link capacity.
Okay.
The other one which worried me,
Yeah.
how do we make sure that our data or the algorithms that we develop and so on. But so far, it looks like the different companies which are, using, cloud computing have been able to do that. But that was one of my first worries, when I was director of GPI.
Yeah, it's definitely an interesting challenge. Like you said, it's kind of a black box from the user's point of
That's
view.
right. Yeah. If you have your own computer, you can protect it. But when you are using a computer 10,000 miles away, you want to make sure that they have the security that you need.
What advice would you give to some of our younger scientists and researchers who want to pursue a career in these fields?
Yeah. Well, my advice for all people is a little bit what you mentioned at the beginning. Just stay curious.
Yeah.
Be willing to try new techniques. Don't be afraid of failure, because that's how you learn. That's always an issue, because people are worried about failure. And I keep telling them, no, that's okay. If you really want to push the limit and you are doing something for the first time, it's not going to work every time. And be willing to lean forward and try something which seems even very, very tough. And particularly for, I see it in the students that I mentor and work with, that in order, if you're going to do a discovery, it's not going to happen because you do easy stuff. It's going to happen because you are trying really tough, because you do easy stuff. It's going to happen because you are trying really tough. And therefore, there is a possibility that things might not work. But the critical thing is to learn from it. We had failures at JPL. We crashed spacecraft on Mars a number of years ago, but we didn't give up. After the crash, we went and said, okay, let's find out why did it happen, even with all the work that we did and all the testing, it still didn't, there was a problem, on it. And we ought to learn from it. So fortunately, in the last 15 years, we haven't had any crash. and it's based a lot on learning from the one which failed. So the key message to the researchers and students and everything in life is don't be afraid of failing, as long as you learn from it. You don't have to.
That builds on what you mentioned about the lessons learned.
Yeah.
That we need to constantly track these lessons
That's right.
learned.
That's right.
As we progress. So I think we're about out of time. If there's any additional questions from our audience here, or we could just, maybe there's one last question. You mentioned some exciting space missions. I'm curious to see how we can get more Saudis involved. How we can get more Saudis involved. So I think there's a lot of opportunities with tax. We've done.
I think a key advance recently is the fact that you formed the Space Commission a few years ago. And I'm involved as an advisor, but on the advisory board for the Space Commission. So that reflects that the kingdom now has big ambition about using space for human benefit. And I think by working agreement between Saudi Arabia Space Commission and other agencies, be it NASA or ESA or other agencies, that will enable more collaborative effort on the internet. So to give you an example, every mission, when I was director at JPL, we flew like 25 missions during my director time. Every mission had international collaboration. We had either this one provided by other countries or scientists from other countries involved with us or technology. So I think as the space activity in the kingdom matures more and you work agreement with other agencies, I think there are opportunities for collaboration, both ways. Things developed here, go on other missions, and particularly now with the Artemis program that the US has about exploring the moon, having stations on the moon, and then from there going to Mars. And I think Saudi Arabia is a partner in that area. So that's going to enable people exchange, which is critical, for exchanging ideas and doing that. So I think there are opportunities of collaboration as your space program matures.
Right. Excellent. Thank you so much. It's been a pleasure sitting with you. Always nice to see you
It's
here.
my pleasure here too.
Always nice to see you here in Kingdom.
Yeah, thank you very much. It's always a
Thank you
pleasure.
Thank you everyone for joining. Thank you.